Hello and welcome to my science tutorials. In today's video, we are going to be looking at Oxymercuration Demercuration reaction. Before we begin, if you are new to my science tutorials, kindly consider subscribing and pressing that notification button so that you don't miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So let's begin. What is an Oxymercuration Demercuration reaction? Now, this reaction is another method of converting an alkene into an alcohol. Now, in our previous tutorials, we look at how to convert an alkene into an alcohol, and we use the acid catalyzed hydration. Okay, that is we add water in the presence of an acid catalyst, and then this converts an alkene. That is, if we have an alkene of the form this, okay, and we add this reagent, we can convert it into an alcohol. Sorry, this should be a single bond. Then we have this, and we have our OH, and then our hydrogen attached. Okay, so this is our alcohol. And then we said in that tutorial that this reaction goes via the Markovnikov addition. That is, the OH over here is attached to the most substituted carbon, and then the hydrogen goes to the less substituted carbon. Now, in Oxymercuration Demercuration reaction, for the oxymercuration part, we add mercuric acetate, that is this mercuric acetate in the presence of water to produce an intermediate. Okay, now after we get that intermediate, which we are calling the mercurinium ion, we now add this is the first reagent that you add. The second reagent that we add for the demercuration part before we get our alcohol is sodium borohydride. Sodium borohydride in the presence of a base such as sodium hydroxide. Okay, so let's look at what actually happens. So in case we have an alkene of the general form like this, okay, then we add our mercuric acetate, that is this OAC2, in the presence of water, we get an intermediate that looks like this with the OH group attached, and then we have this, then we have the mercury, then the OAC group attached over here. Now this group over here is what we are calling the acetate mercuric group. Okay, so this group is the acetate mercury group. Now when we have the OH, the hydroxy group, and then the acetate mercuric group attached to the alkene, okay, all we have to do is to add the second reagent, that is sodium borohydride, in the presence of a base, a strong base, and then the sodium borohydride in the presence of a base reduce the acetate mercuric group to just hydrogen, and then we get our alcohol. Okay, so what is the difference between this oxymercuration demercuration reaction and then hydration? Now the difference is the fact that in hydration we produce a carbocation before we get our alcohol. Now the problem with producing carbocation is the fact that during the reaction, in order to achieve stability, the carbocations can rearrange. So in case we have a secondary carbocation produced, and then there is the tendency for the reaction to produce a tertiary carbocation which is more stable, the reaction will go that way and produce a tertiary carbocation before we get our alcohol. Okay, so in the end we may get less yield when we are using the hydration or the acid catalyzed hydration. Now the oxymercuration demercuration reaction, we don't produce any carbocation intermediate, so you can see that the yield, if we use this oxymercuration demercuration reaction, is very high. Okay, now things that we need to note of oxymercuration demercuration reaction is one, you could see that when I was writing the product, the OH group is attached to the bottom of the first carbon, and then the hydrogen group is attached to the other side of the second carbon. Okay, so that is, they are not on the same phase, they are on different phases. Okay, so in terms of stereochemistry, The Oxymercuration Demercuration reaction is an anti-addition. That is what we add the OH group and then the hydrogen to what opposite sides of the alkene. Now, secondly, in terms of what regiochemistry, okay, that is which group goes to which carbon. This reaction goes by what? The Markovnikov's addition. Markovnikov's addition. That is to say, the OH over here is attached to the most substituted carbon, and then the hydrogen goes to the less substituted carbon. Okay, so let's have a look at what the mechanism for this reaction so that you can understand what I mean. So let's write the mechanism. So we have, let me use another color. So let me use green. Okay, and then let me use black to continue. All right, so if this is our alkene, now the green carbon over here, I'm using green because I want this carbon to be what? The most substituted carbon. Okay, so the green carbon over here is the most substituted carbon in this case. Okay, now if we have this, okay, if we have this, then we add the what? The mercury acetate, that is this, to it in the presence of what? Water. Okay, before this reaction can go to produce the intermediate, which we are calling the mercurium ion intermediate, something has to happen. Now the mercuric acetate we have over here has to what? Undergo dissociation. Okay, so the mercuric acetate over here, OAC, will undergo dissociation to produce what? Ions. So it will produce this ion. The mercury has a lone pair, so it will produce this ion and then another ion, this ion as well. Okay, so once these ions are produced, this particular ion over here, okay, which is containing what? The acetose mercuric group, the acetose mercuric ion. So this is the acetose mercuric ion. Now this ion will now come and attack the alkene that we have over here. So let me rewrite the alkene. Okay, so this group comes, okay, then we have our positive charge, then we have the lone pair, then we have this. Okay, now we know alkenes have what? Electrons that are delocalized in their pi bonds over here. So the double bond will attack the positive center, and then this carbon, this lone pair, will attack this carbon over here. Now we form what? A ring. So the ring looks like this. So we have our carbon, single bond carbon, and we have this, and this. Now this now attached to the mercury is this bond, and then the lone pair over here attaching to this carbon is this bond. So we have the mercury attached to it, and then we have what? The OAC group attached to it, and then the mercury now has what? A positive charge on it. Okay, so this intermediate is what we are calling the mercurium intermediate. Now remember, this reaction is what? An electrophilic reaction. Okay, so now that we have this, okay, water now comes to attack. Okay, now if the water is going to attack, the water will attack what? The most substituted carbon, which I'm using the first carbon that I use the green for as this. So okay, I'm assuming this is still green, so this is our most substituted carbon. The water will now attack the most substituted carbon, okay, because this reaction, like I said, goes by the Markovnikov's addition. So when water will attack, it will not attack through this phase because this group is a bulky group. Okay, so it will not permit for water to attack through this phase. So water has no option but to attack through the other phase or the anti-phase. Okay, so water will attack this carbon through the back and then breaking this bond onto the mercury. So we now have this as our product. So we have this, and then we have this. Okay, so the water that is coming will not be at the top over here, H, and then it will bear the positive charge. Then we have this attached to the second carbon, we have this and this. Then the mercuric group, that is this OAC, will not be attached to this side of the carbon. So already we can see that even though we have this form over here, we can see that what the OH that we are forming, the potential OH, is at the other side of the alkene, and then the mercuric group is also at the opposite side of the alkene. Now that we have this, another water molecule comes, okay, to pick up a proton, releasing these electrons onto this carbon, oxygen. Now when that happens, this is what we get. Okay, so we get our carbon bearing the OH group now. Then we have the bonds here, and then we have this, and then we have the mercuric group over here. Okay, so now that we have this, let me continue on another page. That is, we have this OH, this with the carbon, this, and then what, this group OAC attached to it. So now that we have this intermediate, we just add what, sodium borohydride in the presence of what, a base. Okay, so if we add this, what the sodium borohydride in the presence of what, a strong base, does is what, it replaces the mercuric group over here with what, hydrogen. Okay, so if this, and this reaction is what, is a reduction reaction, and that is the demercuration part of the reaction. That is, we are removing the mercury over here, so the name demercuration. So if we add the sodium borohydride in the presence of a base, then we now get our alcohol looking like this. Okay, so the acetose group over here will be replaced by what, hydrogen. Okay, and then this is our alcohol, or our product. This is our alcohol, and we can see that what, in terms of what, stereochemistry, it is what, an anti-addition. That is, we are not adding the OH and then the hydrogen to the same phase. That is in terms of what, stereochemistry. And in terms of what, regiochemistry, that is the point of attachment, we are adding what, the OH group to the most substituted carbon, and then the hydrogen to the less substituted carbon, and that is what we call what, the Markovnikov's orientation or addition. Okay, so with this brief introduction to what oxymercuration demercuration is, let's have a practical example of how this reaction actually goes. So the first one we want to look at what is what, the oxymercuration demercuration of what, propene. Okay, now this is the structure of propene. CH3 doubly bonded to carbon, then hydrogen over here. All right, so from here we are adding our ion over here, the mercuric ion over here, that is this OAC, plus then with the electrons lone pair on it. Okay, so the double bond will attack the positive center, and then the lone pairs will attack this carbon, so we form this product. So we have the hydrogen here, and we have the CH3 now here, CH3 here, then we have the single bond carbon, we have the hydrogen here, another hydrogen here, then we form the cyclic bond over here, then we have the mercury here attached to the OAC group, and then it bears the positive charge. Okay, so from here water now comes. Now when water comes, because what, the mercuric functional group has taken control of this side of the reaction, the water has no option but to attack through the opposite side. Now between these two carbons that initially bears the double bond, which carbon is the water going to attack? Because this reaction in terms of what, regiochemistry, goes by Markovnikov addition, the water will attack the most substituted carbon, which is this carbon, because what, it has one alkyl group attached to it, and this carbon has two hydrogens attached to it. So it means one of the lone pairs over here will be used to attack this carbon over here. Okay, so once that happens, we get a product that looks like this. Now this bond will break, releasing the electrons onto the mercury. So when that happens, we get the carbon. Now I'm shifting this CH3 to the downside, so it will come here. Now the hydrogen will now be here because the water is coming to occupy the top. So we now have the water here, okay, with a positive charge. Then we have this, okay, and we have the hydrogen at the top, the hydrogen here, then the acetate mercuric group over here. Alright, so once we have this, another water molecule will come, okay, to pick up a proton, releasing the electrons onto the oxygen over here to form the OH. So from here we get this product. We have the hydrogen, then we have the OH at the top, and we have the CH3 at the bottom, and we have this attached the carbon with the hydrogen, and then the acetate mercuric group over here. Now that we've reached this stage, all we need to do, or this stage, the oxymercuration part has been done. That is what the addition of what mercuric acetate in the presence of what water has been what completed. Sorry. So all we need to do is to add what sodium borohydride in the presence of what a base, and that will what replace the acetate mercuric group that we have over here with what hydrogen. And so when we do that, this is the product that we get hydrogen here, and we have our OH over here, then we have the CH3 group at the bottom, and we have this we have the hydrogen here, hydrogen over here. Okay, so you could see that the OH that we are adding is at the top, the hydrogen that we are adding is at the bottom. Okay, and so this is our product, and the name of this product, this is what 2-propanol. Okay, and like I said, unlike the direct hydration of an alkene in the presence of a strong acid, oxymercuration demercuration produces alcohols of better yields, since carbocation intermediates are not produced in this reaction. Okay, and then also the reaction conditions for this reaction, okay, is not harsh as in what hydration reaction, because in hydration reaction we use what strong acid like what H2SO4 to do the hydration. Okay, so maybe we add water in the presence of what H2SO4, and this reaction condition is very harsh for producing what an alcohol. But then in oxymercuration demercuration reaction, a milder condition is obtained. But then we need to note some disadvantages of this reaction. That is, the disadvantage, however, is that organomercurial compounds are highly toxic. That is what any compound containing mercury is very toxic, and hence care must be taken when handling them, and then we must also dispose of them properly. So when we are carrying out this experiment, we need to be careful, because the reagent we are using is very harmful, or is very toxic. All right, let's have a look at another example of oxymercuration demercuration reaction. So the example that we have over here, okay, we have this as our alkene. We have CH3 attached to a carbon here, and you have the double bond CH over here, and then we are adding what? One, we are adding this in the presence of what? Water. And then secondly, we are adding what? Sodium borohydride in the presence of what? A base. Okay, so we are to write down the product of this reaction. All right, so let's write the mechanism for us to be able to get the product. Okay, so first of all, we know that the mercuric acetate group will dissociate. So we have this giving us this, will now dissociate to form this OAC plus with the lone pair on the mercury over here, okay, plus the OAC ion. Okay, so from here we know that from here the reaction will now occur. So we have the alkene. This is the alkene with the hydrogen here, hydrogen here, hydrogen here. Then we have what? Carbon bearing what? CH3, three of them over here. Okay, so this ion will now come for the electrophilic attack to occur. So the double bond will attack the positive center, then the lone pair will attack this carbon over here. So we get this as our product or our intermediate. So we have, sorry, let me clean that up. Okay, all right, so we have this hydrogen also at the top over here. Then we have the carbon bearing what? The CH3 group over here. Then we have the two bonds that are now formed between these two carbons, and then the acetose mercuric group. So we have this attached to what? OAC, and then this has the positive charge over here. Okay, so now that we have this, water now comes to perform its role. So water will now attack the most substituted carbon, because we say this reaction goes by what? Markovnikov's addition. So water will attack this carbon because it is the most substituted carbon, and then when that happens, this bond will break, releasing the electrons onto the mercury group over here. So you can see that we now have this. The water will now occupy the top over here and have a positive charge. Then the hydrogen will shift to this side. Then we have the carbon with the three methyl groups now over here. So let me write that as this: CH3, 3. And we have carbon with the hydrogen, and then this group over here, the mercury, that is the acetose group over here. All right, so from here another water molecule will come and then pick what? A proton from here, releasing these electrons onto the oxygen over here. So from here, this is what we get. We get what? Our carbon now having the OH group as we want, hydrogen here, then we have the CH3, then we have what? Let me extend this bond a little, this, and then the mercury, and then the OAC group over here. Okay, so now that we've reached this intermediate, all we need to do is to what? Add sodium borohydride in the presence of what? A base, which will to replace what? The acetose mercuric group over here with what? Hydrogen, and then we'll get our product where hydrogen will be here. So our product will be what? Carbon, then we have our OH group over here, hydrogen here, then we have CH3, okay, 3 of this attached to this hydrogen, okay, and then hydrogen over here. But note, the new hydrogen that we are adding is the one at the bottom over here, and then what? The new hydroxide group that we are adding is the one at the top over here. So this product is the name of this product is what? 3,3-dimethyl butan 2-ol. So this is 3,3-dimethyl butan 2-ol. Okay, and then the yield for this reaction is 94%. Okay, so this is a very good yield. Whenever you perform an experiment and you get a yield such as 94%, that is actually a very good yield for you to continue with your experiment. So thank you so much for watching. This is how we perform the Oxymercuration Demercuration reaction. I know this tutorial is just a very simple one. In the future, we'll be creating more sophisticated tutorials where we'll be looking at major alkenes, and we'll be adding the acetose mercuric group, and then we'll be performing the Oxymercuration Demercuration on alkenes with what? The line structure, instead of drawing this condensed and then open chain structure. So we'll in those tutorials we'll be looking at what alkene groups, where we'll be looking at benzenes containing double bonds and how they react in terms of what oxymercuration demercuration to produce what alcohol. So thank you so much for watching, and I will see you in the next video. Until then, peace. Bye bye.